Good afternoon, everyone. Thanks for coming to my defense. My topic is wireless network virtualization. So wireless network virtualization broadly is basically a systems approach by which you can house multiple virtual networks on top of a single physical network. So before I delve into the details, I'll just specify a few terms which I'll mention throughout the thesis, throughout the presentation. There's a mobile network operator, an MNO. It's basically a physical operator like AT&T or T-Mobile who actually owns the hardware, like base stations, access points. And these guys lease out capacity to MVNOs. MVNOs are mobile virtual network operators. So mobile virtual network operators take this capacity and provide service to their clients. So MVNOs exist, and like why do they exist? So we were just trying to think this, but so you have a large number of wireless users, and the number of wireless users is on the rise. So in this case, if you have very different service requirements from the user side, then MVNOs basically allow you to customize this sort of service. So each MVNO can just have a different model by which they provide service to the users, and then this is all. So there's a list of MVNOs online. Here are a few which picked up from the website. So why do we virtualize? So the thought here is basically if MVNOs lease out capacity from the mobile network operator, and if that is done by leasing entire base stations or using the entire spectrum, can we share individual components of the network so that we can have better utilization of the hardware? So can we share base stations or can we share access point based networks like hotspots among multiple MVNOs to get better utilization? The other motivation for this study is an application in test beds. So if you have, like we have a nationwide initiative called Genie, NSF Genie project. In that project, you have a nationwide virtualized testbed being set up so that you can run multiple experiments at scale. So in that case, if you want to test experiments on the wireless edges, and you want to test an experiment from end to end, like from the wired links to the wireless links, in that case, having a virtualized edge will be useful. This is the layout of the thesis. I'm going to be talking about the blue parts which you see over here. So the three parts are basically how to virtualize an access point based, a hotspot based network, WiMAX base station, and then I'm going to talk about how you can do mapping or resource allocation across a virtualized network. So this is the first part. So the motivation for this is, say if you go, for example, to an airport where you have a common coverage area, and then if you have multiple vendors around and if they are trying to provide wireless coverage or Wi-Fi coverage to a common set of users, then in that case, if everybody ends up having a hotspot or if everybody ends up having an access point for themselves, then in that case either you'll run out of the common hardware which you can deploy at that place due to some restrictions by the airport authorities, or you will run out of the orthogonal channels available, right, if everybody tries to do the same. So in this case, can we share the access points, right? So one simple approach to this would be just have a common access point and then say, okay, not everybody's users can connect to that access point and have service. Like Starbucks, Dunkin' Donuts, everybody will say, okay, connect to that one access point and it all works. But in that case, you can't have any kind of customization. So you can't have any sort of policies which are set across two different networks, which everybody might want to do. And then you don't have isolation across these networks. So our approach to this problem is by trying to virtualize the access point. So if you have two different independent virtual networks, so if this is one ISP and this is the other ISP and if they have their clients, then you can map them onto a single access point and have this access point emulate two different virtual access points and have these clients connect to each other. So here are a few design challenges we face. So one part is having group traffic isolation. So if you have these two different networks, virtual networks existing together, you want to make sure that they get enough resources and there is no, like, they don't eat into each other's resources. And we are trying to do this for uplink, partly because like we have shown how this can be done for downlink on our base station project. And then the other part is we have motivation which shows that the uplink traffic is on the rise. So this was picked up from a white paper which shows that that blue part is basically the P2P traffic, and you can see that that is on the rise. Apart from this, there was a recent Cisco paper, which I have not put in here, but I have a citation for that, which shows that the mobile video generation, like client-side video generation, is going to be a major source of traffic later on. So that is our motivation for looking at uplink traffic isolation across groups. And we want to do this without having any kind of changes to the MAC. So we wanted to be able to run on conventional 802.11 based networks, so that you can still use other features to customize your MAC, like you can change parameters on the MAC layer and everything still works. It should scale and it should be easy to deploy, and it should work with off-the-shelf hardware.
So Gautam, does that include downlink and uplink traffic together?
Yeah.
When you say internet video to TV, it's from some DVD player to TV, but that won't be really IP. What is internet video to TV?
I think they were talking about IP traffic on this.
Down.
Yeah. There's actually another plot which shows basically the uplink traffic, which is increasing. That's a Cisco Wi-Fi.
Wireless traffic or wired traffic?
That I'm not sure. I don't think it's wired. I don't think it's just wireless. I don't think it's combined either.
It's combined total internet traffic, including downlink and uplink. Meaning, of course, on the internet there's no difference.
As far as I know.
On the wireless side.
Yeah. This is the main related work in this area. We have basically it's in two parts. One part is looking at infrastructures which allow you to manage an access point based network, and another part is basically how you can have traffic isolation across groups. Like the first part, basically dense AP paper was basically showing how you could do load balancing across different access points. There were other papers which showed how you could use virtualization on the client side to basically create two or more, like multiple virtual interfaces on the client and then connect to different access points and improve your throughput on the client side. And there were some experiments on the Orbit Testbed where we try to see how multiple experiments could coexist. But these experiments really don't match up with what we are doing. They're different. On the isolation part, people have tried to use the hooks in the EDCA mechanism, that is changing contention windows, changing AIFS time slots, changing transmission opportunities, and then trying to maintain fairness or isolation across groups. But then in that case, you don't have any kind of hard and fast guarantee, because first of all, that is difficult to compute the numbers, and then even in that case, when you come up with those numbers, you can still pump traffic and end up interfering with each other. And all of these are done through simulations. Like all of these papers which we have cited are done through simulations. The implementation part was a time-based regulator, which was implemented by a group at MIT. And what they showed was basically by assigning tokens, you could control the uplink traffic. And they try to do that for different physical realities. But then again, that you have a lot of control over it, first thing. And then the second thing is we are trying to do it across groups of flows, not an individual flow. And then the third thing is we are doing, what we will try to do will be effectively to show that we can work independent of protocol, packet sizes, offered loads. So those will be.
So the standards will be something similar to PCA.
Yeah, it is very similar to PCA. And it is also effectively changing the MAC and CA. This is our architecture. So we have our access point will emulate multiple virtual access points for different networks. We'll also run a slice traffic accounting mechanism on the access point, which will determine the total overall airtime for every group or every slice. And then we'll send out a broadcast to the clients telling them, okay, you have to stay within so and so limits. On the client side, we will receive this control information and we implement a shaper, a traffic shaping mechanism, which basically on receiving this control information limits its outbound traffic. So there is no change in the MAC, everything behaves as is, only we are limiting the load on the MAC. So what sort of control information should be sent from the access point to the clients? So there are different things which you can send, and then you will have different performance based on that. But we wanted something that has least overhead, something that scales independent on the number of clients within a group. So if you have 50 clients within a group, you shouldn't have to send 50 clients independent control information, right? So it should be some sort of a broadcast parameter, and it should enable local decisions. So despite being a broadcast parameter, despite sending the same thing to everyone, everybody should be able to infer it and set their limits accordingly, independent of what is happening everywhere else, just based on local conditions. So the measure we use is basically the maximum fraction of airtime which every client within a group can use. Right. I'll come to it. I mean, I'll explain that through an example.
Going back to this, there's some control overhead as well as you have to also run a special client application, right?
Yes, that's true.
That's an overhead.
So, yeah, the control information.
You cannot change the MAC. There is an overhead involved. In
that is always true. So actually, in the related work, right, they had this overhead plus they were changing the MAC. So the sort of difference we have is we are limiting the load and we are not changing the MAC. But we have this small control overhead that, okay, despite, I mean, it's just a broadcast. So you can actually couple this with a beacon. And every virtual access point has an independent beacon. So if you couple it with that, then you clearly don't have an excess overhead.
So let's stop and try to understand here. What are you virtualizing? You're virtualizing, or what are you trying to focus on? You're trying to focus on the traffic coming from the set of clients up to the base station, or the base station down the set of clients? That's question one.
So it's uplink.
Uplink, right? So, and now some of these are going to be Starbucks, and some of these are going to be Pete's Coffee clients.
Yeah.
And you're going to tell them, hey, you Starbucks client, you don't get as much as you want.
Mm-hmm.
And so when a user goes in with this laptop, what does that mean? That means he's going to have to actually download, I think, as he was asking.
Exactly. So it has to
a
download.
new,
So it has to download. So typically, like, it is either like in such systems, right, they either do a gateway-based sort of authentication and then they try to do some sort of isolation, or like this. So basically, if you install, you will have to install a client connectivity software, which the access point will say, okay, if you want to connect to my access point, download the software and connect to me. Or you, I mean, eventually, like, we were also looking at this as some sort of browser plugin, but we haven't thought of that. But that's basically it. You need some software on the client side to make sure that you can control, because that is the only way you can limit the traffic going on there from the client side.
So the other question is, as opposed to doing something like this, doing a CTS, right? Related to a CTS or some CTS type of thing with the client's backups, for example. Would that work, and with some NAV adjustment or things like that? I think you say something about the thesis was not very clear. What
That is also an option, but basically, if you do a CTS on a per client basis, right, and if you have,
so expensive.
yeah, it's very expensive. It does not scale. And then there were also other ways I was looking at. Basically, you could do this based on changing the protocol feedback, right? So if you have TCP from every client, then you could also drop certain acts and then change the contention window indirectly.
Okay.
Yeah, but that would be again protocol dependent. So that's why I eliminated that approach. But that is another viable approach of trying to do something like this. So that is something even people are starting to look at now.
Another question is this: the quota is in terms of the edge.
It's an airtime flash.
So it's not really through.
No, it's airtime flash. So actually, I'll show an example, and that will be.
So these clients are all going to share the same SSID under the airport's Meta wireless.
So they get their own SSID. So the clients want connecting to Starbucks will see a Starbucks SSID. Clients connecting to Pete's Coffee will see a Pete's Coffee SSID. And that is a feature which is actually provided by the driver itself. So there are, like, most of these newer softwares, they can emulate virtual access point in the driver itself. This is the controller algorithm running on the access point. We are calculating the quotas per slice, figuring out if there are, like, if you are exceeding or below the quota for that slice. And then we basically have a block where you can calculate the maximum fraction of airtime which every. So we calculate where how much quota each client can take, right? And this is a pluggable model, so you can plug in any kind of algorithm over here and then it is broadcast.
So in a system where there is no virtualization, I don't have any quotas, do I?
No. So actually
now
you can
in
do
a
it for
system
the.
where we are doing virtualization, I'm going to have to take upon me this forced quota system.
Yes.
So I go from being free and unfettered to now fettered,
So that
because
you don't
the
end up.
airport won't allow me to have two access, or won't put up two access points.
Yeah, either that or you don't have enough. So if you are operating in P mode, right, you'll have only 3 orthogonal channels. And if you have more than 3 vendors, then everybody will end up interfering with every vendor.
Yeah, but usually Pete's is at one end of the airport and Starbucks is at the other end.
So
Right,
I was
so
I was thinking of a scenario where there is a food court in the middle and then you have multiple vendors competing on the side. Or say like Boingo has, right, they have access points deployed around the airport. But if there are more than one ISP, right, why just Boingo can get to provide service there? Maybe someone else wants to do. So this is an example, and in this case, right, what I'm going to do is I'm going to scale based on the number of clients. All it does is it figures out how many clients are there in my group, and then based on, and you get all of this information from the drive. So I'll explain the implementation later. So if these two access points are there, then I'm saying that okay, I'll give equal allocation to both slices or both groups, and I'm assuming that for now, for this example, that all the clients have an uplink physical layer rate of 10 Mbps. Right? And everybody has saturation traffic. So in this case, two clients connect. They get this broadcast parameter which says, okay, you can have half the total airtime, right, at which you can transmit. So they figure out, okay, my physical layer rate is 10 Mbps, so I can transmit at 5 Mbps so that I only occupy half the total airtime, right? So this works out okay.
So what exactly do you mean by a 50-50 airtime quota? Say if access VIP2 has 0 clients and VIP1 has 10 clients, then the 10 clients from VIP1 can only take up 50% of the airtime.
So that is the way it is right now, but this can be easily changed because all it is doing is just calculating the fraction. And I'll show actually in the next. So this is the base algorithm. And the next algorithm, what we'll show is, and we actually show it for different loads, but the same logic can be extended across slices. So this is just a policy decision, right? So if you are paying for half of the access point, you want to make sure that whenever your clients connect, even if sporadically or whenever they connect, they get the entire quota. If on the other hand you say, okay, I'm willing to pay less, I want a flexible quota, that can be easily changed over time.
What would it pay less in this case?
Sorry.
So I'm thinking more about the case where the airport is not used by VIP, the access point is not used by VIP2, or shouldn't I get the whole access point in that case? Maybe that will
If you have enough clients, then it would make sense to get entire access point.
So can you do that?
So yeah, if I provision that in the beginning, you can. Or you're saying dynamic? Is that what it is? That should be, that is
So
very
if there's bandwidth that's unused for the other virtual access point,
that can be.
why not use it to the...
That is just a policy decision I made.
One that requires it.
That is just a policy decision I made in the beginning. That if you assign these quotas, they stay the way. But I mean, it's just a calculation that changes the fraction. I can always change the max limit from 0.5 to 0.7 or 0.8, and everything will still work.
So this
If you would make it more flexible, then I think we would also have some of these concerns that you raised.
So I guess the C slice could be a function of both the number of clients per ID. That should be easy to do because you know how many clients are connected.
Yeah. So that is what I'm showing.
That's one thing, right?
Yeah.
Here it's just fixed. I mean, there you could do that. And the second thing is that if you know the rate, I mean, as long as if you consider that the rates are reasonably constant, fixed, you know, the clients are stationary. Then maybe if you know the rate, you could, you know, if it's reciprocal, if it's a reciprocal down the top, you also know the rate, so probably you could even make it proportional to the fraction to control the throughput rather than just the airtime.
If you know the rate, but actually that's the coupling which we did not want to have, because if essentially this area is spread out and everybody has different rates, then you have to end up keeping all the track of physical layer rates at access point, right? So in this case, I have the advantage that okay, I don't have to do that part. I'll just broadcast an airtime fraction, and everybody will figure out, okay, this is my rate, this is my packet size. So to have this rate and this packet size, I can support so much amount of load by using only so much airtime. So that is my max load on hand.
So it's based on
But
number.
that is another option, though. You're right.
So that's based on number of client for each of virtual operator, and you give a fraction of the divided the number of
Yeah, for now.
client.
Yeah, in this example. So actually, let me just show.
Their load are different also. So for
That-
the client
getting into
within,
that. That is in the next slide. So in this case, right, when this client connects, then the access point figures out, okay, there are more clients on this route. So it is going to scale the maximum fraction to 0.25, right? And in that process, then these guys end up sharing the capacity. So this is implemented by, we have to install a client-side software, and these are the two components, basically a traffic shaper and a controller, which controls the rate at which you are shaping outbound traffic. This is how these components look like. So this is the traffic shaper. It pulls out packets from the kernel and separates control traffic, MAC control traffic from IP traffic. And then this is the outbound IP traffic. And you can limit the rate at which you're shaping outbound IP traffic with this control daemon. What this daemon does is it queries the driver, figures out what sort of packet size, what sort of average packet size you have been using over the last interval, and what is the physical layer rate. And then based on that, we can determine the rate at which you're shaping, based on the airtime which you get, the fraction which you get from the access point. So I'm going to present some basic results. These results are still an improvement over all of the related work which I've shown out there, because they've done it only for one physical layer rate and UDP traffic.
What happens if it's, the traffic is not backlogged?
I'll come to that in the next.
So can you explain the component that blue box within the board?
This one? Yeah.
So how do you figure out what rate you need to shape at?
So that is available in the rate table in the driver. So the driver maintains a rate table, and you can get an information about that.
So if I'm understanding you, you have some requirement 50% of the airtime.
Mm-hmm.
And
So
now you need to shape your traffic. The airtime of your packets depend on
The packet sizes.
actually you should be explaining to us.
Yeah, I'm sorry. So I was actually going to get to that. So the airtime of the packets depends on your physical layer rate and your packet sizes. Right. So if you have smaller packet sizes, you have more CSMA overheads and more PHY and MAC overheads associated with that. So what we did was we did a basic calibration study, and we figured out for different rates and different packet sizes what sort of airtimes do you require. Right. So based on that, I have an idea. Okay, you know what, you can. And then all I'm doing is I'm doing a lookup every day. I'm just saying, okay, you know what, X is the physical layer rate, Y is the packet size. What is the max airtime I require per bit of effort? And then I can scale that. I can just divide I can just find out, okay, max fraction is so much, current, like this is the overhead. So I can send so much amount of.
How do you know at which rate the packet will be transmitted?
So that is true. I mean, I don't know exact rate at which the packet will be transmitted, but I'm assuming that, like, there is sort of a pseudo mobility, and then the rate doesn't change drastically. And fairness, right, what we are doing is basically a long-term metric. So on a short term, you might see some like.
Does this table that you have there get adjusted dynamically?
This table, no, the table is actually statically calculated. What gets calculated is which entry I'm looking at.
Packet error rates and number of retries increase. And
So that is, so if retries increase, right, that is a different story. So I'm assuming that since all the traffic is going to the access point, right, everybody will get affected equally. That is an assumption I'm making. Because the receiver is on a single access point.
it could be very, very independently.
I agree, but that is the assumption I have, right? But there is another option.
The algorithm won't work.
So there is another option actually, which we haven't used. There are MAC retries which you can get from the driver on the client side. So if you get the MAC retries, you can scale the amount of airtime appropriately. So basically, if you know for sending every X number of packets, you have to have so many retries. You can scale the amount of. I mean, that would be one way to do that. And we haven't done that, but that is an option. So these are the results. So these are for the two clients sending uplink traffic. This is without a system. This is with a system, without a system, with a system. Same here, without, with. This is done for packet sizes, physical layer rates, and offered loads. And basically what we see is, in this case you don't see a very big difference, but it tries to bring the total quotas to 50%. Even in this case, And in this case, what happens is, the offered load for the client one is less. It's just 6 Mbps. So in this case, what you pointed happens, right? You end up shaping this guy at half the traffic, even though there is total airtime available. So we'll try to address that in the next slide. In this case, in the next slide, we are showing how you could do weighted fairness, right? You could have 1090 allocation, and what we are showing is something similar to what there was earlier, but it is scaled now. So first slice only has 10%, other slice has 90%. And then again, you can do it independent of packet sizes, offered loads, or physical layer rates. So basically just showing that the measurements work with this thing. This is a modification over the base algorithm. And in this case, what we're trying to do is update airtime usage based on load on the slice, right? Not just based on number of clients, right? So one approach is just figure out, okay, I'm using X amount of airtime for this slice, and then this is below the quota. So I have some surplus available, so I can increase. But by how much do you increase, right? So you could make a guess. I mean, you could just gradually start increasing and see what happens. But it turns out that we can make an educated guess in this case, basically by figuring out how many clients are currently saturated. So if I increase the airtime fraction by say 0.1, it is going to increase depending on how many clients are being currently shaped, right? So if I can dynamically figure out how many clients are being shaped or who are saturating, they're trying to saturate the link, then I can scale that outbound load, outbound fraction accordingly. The way we are figuring out how many clients are actually saturating the link is by learning from previous cycles. So in the previous cycle, if I increased the airtime fraction by 0.1, right? If I went from 0.1 to 0.2, or just a 0.1 increase, right, independent. And if the total airtime usage for the slice increased by 0.3, then I know that three clients are basically trying to push saturation traffic. And using that information, I can scale this, and it works. I can show you an example in the next slide.
So where is this traffic shaping done?
Traffic shaping is done in the client side.
Right, but at the driver, from
It's outside of the driver. It's in the user space. It's an application. So this can also run in a kernel mode, but that's not needed. This can shape at 200 megabits.
So the IP packet is just shaped before they go to the driver?
Before they go to the driver, yeah. Pulling out packets from it.
How are messages sent to this application?
Through Wi-Fi, just broadcast beacons from that. So this is where we left it earlier. We had 2.5 Mbps on each of these clients, and now say the load on this client changes to 1.25, right? So what happens is the overall slice usage drops, right? The controller figures out, okay, now it is not using the entire quota, it is just using like 0.375 out of 0.5. So then you know that you have a residual airtime of 0.125, right? And it figures out using the logic I mentioned how many clients are trying to saturate the link. So it knows one client is actually trying to saturate the link. In that case, it scales this value by 1 and broadcasts this parameter. So what happens is we broadcast 0.375, right? And when I broadcast 0.375, this client figures out, okay, I can go up much more and stay within the quota. So then you end up getting fair division, but you can have higher offer load.
So this 1.25 megaseconds is because there's no backlog.
There is no backlog traffic.
Right? So it's finite buffer.
Yeah.
So somehow the VAP2 figures that one of those clients does not have backlog traffic.
Yes.
They're somehow able to change the size of the residual quota and then add it to the original.
Yes. So it does that basically by learning from the previous cycles. So in the previous cycles, right, if it tried to increase or decrease the quota by say 0.1 or 0.2, right, it figures out how much the total slice airtime usage changed. And it changes in the proportion to the number of clients who are at that limit. Right? And
So it doesn't have to know which client is.
It doesn't care about which client it is, right? That's the way we want it.
So can you do the same for the between the virtual operator?
Yeah, really. It's just a change in one equation. It will do it across.
Right. And then you do.
So what happens if now both clients need lots of bandwidth? How do you ramp it down?
If both clients need a lot of bandwidth, then this guy, so we have left a small margin, right? These guys are not really saturating the entire thing. So if you have 36 megabits, right, we are allocating only until 33 megabits. So this guy still has place, right? And the max fraction being broadcast is 0.375. So this guy will ramp up his traffic. Controller will figure out, okay, this slice is exceeding its quota.
Wait, he's ramping up his traffic, but you just told him not to ramp up his traffic.
No, we have told that you can ramp up only using 0.375 per client. And this guy is using only 0.125.
Okay.
Right? So this client still has a limit. It still has enough traffic it can push in. So when it does, the controller figures out, okay, if somebody's trying to ramp up traffic, I have to cut down this quota. it cuts down by the proportion of clients it figures out are being shaped right now. This is reduced, and then automatically these guys start scaling down. So we have results which show this for static cases, but I have a result which shows this on the runtime. So in this case, right, we have slice 1, client 1, which is staying independent of what is happening on slice 2, with 2 clients connected to the access point, same shown from the example. And this client is saturating the ring, right, basically trying to offer max traffic. And then this client increases its offer load by 5 Mbps every 3 seconds. It increases up to a certain point and then tries to decrease. So what happens is when this client is starting to increase its offer load, the scaling happens and then this client is automatically brought down. And similarly, when this guy's traffic offer load drops, the other client starts getting that capacity.
So it's not as good as not knowing exactly how much a client has gone down from the max and then trying to adjust everybody else, right? Because
I didn't get it.
you went from 0.37, I don't know what it was initially, 0.25 to, it goes down to 1.
It goes from 0.25 to 0.125.
0.125, right? And so you want to give this remaining
125
to other 9, there are 10 clients, let's say.
If there are 10 clients, it is scaled, and if 10 clients are offering saturation traffic, it will be scaled along time.
Right. And
so that is the load issue. So in this case, right, we have a similar experiment, except that one client is doing an FTP transfer that is using TCP, right? So these two plots, right, these two bars, blue bar and brown bar, are for UDP traffic. Blue bar is for slice 1, so that stays independent, constant traffic. So it is offering saturation load, but it is being shaped at traffic. And these two are for the second slice. This is the FTP transfer time, right? And what we observe is as the offer load for the second client in the second slice increases from 4 Mbps to 8 Mbps to 12 Mbps, the FTP transfer time automatically increases so to make room for this client. So we actually also, there should have been something else with this. We should have actually plotted the rates, the overall aggregate traffic throughput rates. And this actually works out to around 11.4 Mbps, while the other one is 12 Mbps. So we see short fluctuations when we do this for TCP, but overall on an average rate, the throughput numbers match up. And this is the final result. So in this case, what we are doing is one client has just one access point has just one client connected, and then the other virtual access point has 5 clients connected, right? And then they are offering traffic as and when, like I'm saying 1, 2, 3, 4, 5, right? These are the number of clients offering saturation traffic. This is the overall throughput which you see in the system, and this is the fairness in the system, group fairness across clients. So what we observe is basically initially when the number of when lesser clients are offering traffic, the utilization with the basic scheme, right, which is scaled based on numbers, is not good enough until you have a large number of clients pumping saturation traffic, which is expected. This is the result which you see with statistical multiplexing. So if you just have all of the clients present and then you have no control, this is the throughput you'll see in the system. And this is what you see when we use our modified algorithm. So what we see is utilization increases dramatically over this. And in this case, we see that this is the fairness without our mechanism. And these two are the fairnesses with our mechanism. So we see almost a 40% increase, 42% increase in the giant fairness index across groups in this case.
So the point of this is to show that
the point is to show that
provide resource isolation and at the same time
you are getting
able to get good throughput and also fairness.
Yeah. So there are other results in the thesis. We have shown a simulation. We have basic system design details. We have some notes on delay performance and static performance, but they are all in the thesis. I'll shift to my second topic. So this is about virtualizing a WiMAX base station. So WiMAX is a 4G radio technology. It has different applications like basically data connectivity, voice connectivity. They are also trying to do IPTV on this. You can also use it as a backhaul link for 2G connections. And this uses OFDMA as a MAC5 layer. It's fully IP based. I'll just give a brief introduction on this side. This is how a basic WiMAX system looks like. You have a wired connection coming in. It comes into the ASN gateway. This is the application service network gateway. And depending on the profile of the base station, you will have different functionality on this piece of box. This piece of hardware. So in this case, our base station is a profile A base station. So radio resource management and mobility management is done on the ASN gateway. And this talks to the base station transceiver system, which consists of an IDU and an ODU. IDU is the indoor unit which takes these packets, signal processes them, and sends the signal to an outdoor unit. The outdoor unit is basically an RF amplifier which amplifies the signal and sends it to a roof-mounted antenna. That's a very brief idea of what WiMAX is. So the motivation for virtualizing a WiMAX base station is similar to what we have for an access point based network. Only the other things are we wanted more programmability in this case. So each slice or each MVNO should be able to control more things on the base station. We should have portability. The other thing is we wanted this as an application for test beds in our project. So WiMAX is essentially all IP, and we wanted to have support for experimental protocol stacks. The other thing is we wanted to have isolation again across multiple slices. This is a brief, like these are 2 or 3 prominent related works. The first thing is multi-WAN base station made by Vanu, and what these guys do is basically they have a software base station which virtualizes flows, but we cannot utilize this solution on conventional base stations because it doesn't work on carrier grade base stations. The other one is a open base station project. It does it for a 2G base station. It runs a software 2G base station but does no virtualization. And the third project is done by our colleagues at NEC Labs. So this is the NVS project, and in this case, the flows are virtualized in the MAX scheduler of the base station. But we do not have, on our setup, we do not have access to the MAX scheduler. So we are doing something outside of the MAX scheduler. And we are also doing other things like emulating base stations, setting up data paths to clients. Okay, so that's the way our project is different. And none of these, so in all of these previous designs, right, they are meant for certain pieces of hardware. What we are trying to actually come up with, we are not really tested it, but what we're trying to come up with is a design which will work across different base stations or existing non-virtualized base stations. So we have a prototype of a virtualized WiMAX base station. We have results which show isolation across different classes, irrespective of different flow types. And we have support for non-IP traffic. In this slide, I'll just show a brief intuitive delay performance of the system and then case studies.
One question.
Sure.
If you go back to the requirements, one more slide. Okay. So you want programmability as well as isolation, right?
Yeah.
So if you do outside of the base station, if you do, for example, traffic shaping, you could definitely probably to some extent get isolation. For programmability is hard.
Yeah,
because whatever scheduler you implement outside of the base station, there is a native base station scheduler that might completely mess up the scheduling.
There is a direct trade-off between the depth in which you can go into the system and the isolation.
Right.
So programmability, yeah, you're right.
So it's not, I think it's difficult to get programmability without really having access to the base station, or somehow you have to turn off the base station's scheduler, meaning make its effect go away.
That is hard because the MAC5, the frame scheduling is it's always done there, right?
For frame scheduler is okay. You can just get rid of, it's as if you send everything through the best effort queue. Or that's not what you're doing.
Yeah, that is.
That's what they were actually doing.
You're trying to do that, right?
That's
That's
pretty much the one.
Yeah.
As soon as other queues are involved, then it gets really hard.
No, we had something going there where you sort of synchronize with the frame scheduler. So you don't really send more data to the MAX scheduler, more than what the frame scheduler can handle. If you can do that, right?
Yeah.
Then you need a lot of feedback
From the base station, which is not existing
It's not
in
easy.
most cases.
It exists, but
No,
not in all the base stations.
Yes, exactly. It's not generalized enough.
Right, exactly.
So in order to virtualize, we are doing 3 things. We want to provide, this is a systems idea, so this is what is done in systems. You provide abstraction, programmability, and isolation. The abstraction part is done by emulating multiple virtual base stations to the clients or to the MVNOs or slices. The programmability part is provided through grid services, and the isolation part is provided by making sure that there is fairness, airtime fairness across these multiple slices. So the non-IP support we are achieving by doing all forwarding on layer 2. We have removed the basic IP forwarding in the system. Isolation is achieved by our VNTS traffic shaping mechanism. And for the programmability part, we have 2 grid services, WiMAX VM and WiMAX RF. This is how the existing network looks like on orbit. We have So this was the conventional WiMAX setup where we have an ASN gateway, a base station, and now we added this virtual base station part, which talks to the ASN gateway. So we have other things by which you can, different interfaces assigned by which you can come into the system and do your experiments. I'll explain each of these components now. So in the virtual base station setup, in that machine, basically we have KVM as a virtualization, full virtualization technology, and we're using that to run multiple virtual base stations. So a user can log into each of these and run their experiments. Each of these will see an interface. Basically, by sending packets to that interface, they can eventually send packets over there. And we are using VLANs for separating traffic in this case. We have two services, WiMAX VM and WiMAX RF. WiMAX VM is a service which is used to control the virtual machines and also control the data paths on that virtual base station substrate. So everything is being done in Fleet, but it is scripted through our services. And WiMAX RF is a service which gives us RF feedback from the base station. On the ASN gateway, the first component is basically we have a modified, simplified, and we have modified control path. This work was done by our colleagues at NEC Labs. So initially we were getting information, control information through a file interface. Now we have stuff coming in through a socket interface, which we can integrate with our system. The other part is all switching is done on MAC addresses now, and we are able to. So we have an isolation part, the VNTS traffic scheduler also running on this machine. We can also run this isolation mechanism in the virtual base station substrate, but it is just a design choice. We add it closer to the base station, physical base station. This is how the isolation mechanism looks like. This is the BTS physical MAX scheduler. This is the controller, and this is the data path engine. We get feedback from the controller, and then we use that information to shape the traffic going into the base station.
So the SNLV feedback from the base station is the MCS information you get?
Yes.
You use it?
Yeah.
For flow MCS?
Yeah. So yes, yeah. And we use that information to calculate aggregate slice rates.
That's supportable. And then you push
That is supportable, and then based on that we are scaling up on traffic.
Right.
Right, so here is a very basic example. If you get physical rates at 20 Mbps and 10 Mbps, and then if you're assigning quotas of 0.5 airtime quotas, then you can scale appropriately. And this rate allocation, like this, we can do this every 300 milliseconds at the fastest, which is limited by the SNMP interface. But rate control itself in the base station with the default setting runs every 200 frames, and 5 milliseconds is each frame. So basically, it happens every 1 second.
So it's still the airtime quota.
This is still airtime. The last part is the base station hardware itself, which we leave in an unmodified state. So this is how we did the evaluation. For the abstraction part, we look at some case studies, and for the isolation part, we have done some experiments just to see if you can have group flow isolation on the downlink, and then we'll also present some intuitive delay.
Question. Sure. If you go back to this notion of getting MCS and trying to figure out and knowing the fraction of airtime you have, you try to figure out how much to shape, right? I mean, how to send the data. So you do the same thing with an uplink Wi-Fi work also, right? You know the rate that's going up.
It is
based on the rate you figure out how much.
It is similar, but there are some differences in this case, because on an uplink, right, the problem is different. On an uplink, I'm doing basically the control is per flow, right, for every slice. In this case, what we're going to do is we're going to do it for a group of flows, in which the traffic is statistically multiplexed from different flows. But we'll say that, okay, you can still, so basically eventually in the experiment I'll show that you can have different layers of schedule. So you can have a flow scheduler run on top and schedule between those flows, and you will have a group scheduler. So we want to show that all of these things still work, right, on a system. You can still do these independently. Over there in the SplitAP framework, we have very fine control. I can just say, okay, per flow I can do something.
So here, so the MCS information, you can get MCS on a per flow basis.
Yes.
But then you probably average it out across all the flows in the group to get an average MCS.
There are 2-3 ways you can do it. You can find a median rate, and based on that you can do it. You can weight it that way, and there are like 2-3 ways to look at it. More ways.
So the control the flow the shaping is on the whole slice.
The shaping is on the entire slice. So it's coming into a single queue, and then I'm shaping it.
And this has to do with the testbed, right? I mean, the idea is slicing is the slice is the visually interpreted.
So this is like what I'm presenting here is just an example. In this case, say if you want to have different MVNOs which are providing customized video service to the clients. So if there is a live event happening somewhere, right? And you have different set of clients connecting to the base station and you want that service. So in that case, instead of transcoding for every single client and rate matching, right? What we are saying, I mean, this is just an example again. This is not the best way to do like this sort of an application, but we're saying that our setup can support this service. And you can have multiple MVNOs which are basically sending videos at different rates to clients. And then the client has an option of selecting okay, which MVNO it wants to connect to and get that sort of a video broadcast. So these are sample results with basic mobility in and around the lab, right? And we're measuring the PSNR which you get at the client. PSNR is a peak signal to noise ratio for that video which you receive. And what we observed is that by adaptively switching between these MVNOs, right, or between these different video signals which you're getting, you will be able to achieve on an average a better PSNR value. So this is just one trace, but we had other traces out of which, when we average out the results, you see at least a 5 dB increase in PSNR of the
This is UDP video, right?
Yeah, this is UDP. Yeah.
On TCP, you can't really measure PSNR. There's no.
No. So yeah, this is streaming UDP video. Yeah.
You can measure PSNR, but TCP also it's just based on what's really good.
So yeah, actually you can buffer on the client.
TCP only is there's nothing wrong. So
But
there's
if
no.
there would be a drop frame according to the buffer schedule, say if the buffer underflows with TCP.
This is on the VLC client.
Yeah, that's fine. But I haven't really seen any PSNR measurement for TCP because the client gets it everything. So unless the client drops something.
So on the client side, if the buffer underflows, like imperfect.
So the next set of experiments is showing isolations. We have one more case study in the thesis, but not presenting that. So in this case, what we have is two slices. We have a mobile slice, which has a client which is moving around, and we have a stationary slice which has a client which is kept in one place. Both of these slices are sending downlink traffic to their clients, and we will measure their performance. So the static client is kept in the orbit control room where there is very good wireless coverage, and the mobile client is moving along this trajectory, and this is the measured signal strength along this path. So that is basically along this whole into that path. So what we want to see is when the mobile client goes into bad coverage, how does this work? Like, what is the downlink performance is? So in this case, what you observe is basically the throughput for the static client also drops along with the throughput for the mobile client. So what happens in this case is, by default, the base station operates in a throughput fair mode, and in that process, it ends up trying to send equal packets for both the clients. And when it is trying to reach this mobile client, it ends up using more resources because it switches to a more robust modulation and coding scheme. So you end up using more airtime, and in that process, you actually bring down the throughput of the other slice, right? So this is not desirable. So when we run our system, what we can do is we can adaptively traffic shape the load or the traffic going on the base station towards the mobile client, and in that process, make sure that we have some sort of an isolation throughout the static, right? The throughput stays. There are other things which I'll explain. So in this case, right, what we did was we had two flows which are best effort of the same class, right? And so if you operate a base station in a time fair mode, which it does, right, in that case you can still have some sort of an isolation. But the base station itself was not built to work. Built to have time fair across slices, different types of flows, right? Because there's no notion of groups of flows on the base station max chemical. So we'll show eventually that we can do this across different types of flows. We have individual results for those, but since I had only a different set of slides which I can present, I'm going to show an experiment which has both like the flow scheduling part as well as scheduling across different priorities of flows. Right. So in this case, what we had was we had two slices. One slice 1, has two clients associated with it, where one is a static slice which has the best effort flow. So that static is just kept in that control room. The mobile client is a very high priority. That is the max priority you can have on a WiMAX base station. That is a UGS client. So that is moving along this trajectory. And then for the slice 2 again we have a static line which has best effort traffic, best effort service. And along with different priorities, what we're going to do is we're going to do flow scheduling within each of these slices. So in one slice, what I'm going to do is we are going to run a round robin scheduler across flows. And in the other experiment, like in one thing I'm doing round robin across these two flows. In the other experiment, I'm going to show how it behaves in the proportional fair schedule. Proportional schedule, not proportional fair. Okay. So first thing to take a look at out of this result is basically these are two experiments, round robin and proportional scheduler. In both cases, approximately you see that the red curve is approximately static. That is the way we are getting isolation. That is the static in the other slice. Static in slice 2. In this case, you see a slight drop because we are not being conservative enough in calculating the average rate for that slice. Right? So if you just take plain average, then you end up with this sort of an interference. But if you scale it appropriately, then this goes away. And anyway, if this is considered as a long-term metric, this is still okay. The other thing to see is basically we are running round robin in this, so we are getting equal packets or equal airtime until the client goes in a bad coverage area. So what happens is the mobile client ends up taking more airtime from the static client from the same slice, and then they again come back. In this case, it is different. In this case, you have the static client getting a good coverage initially, and it is lesser because we are doing a proportional flow allocation. And as the static client goes into bad coverage, sorry, this is the mobile client. As it goes into bad coverage, it ends up taking more airtime from the static client, and then things come back up. So basically, you can do flow scheduling within slices, and this can work independent of the traffic classes which you have.
So this is a question I had earlier, that the max scheduler on the base station could somehow negate whatever you do here.
So it tries to, right? So in this case, what is happening is there's a fixed priorities between flow. So if you have a packet for a UGS client, that is to send out first in any time. I mean, at any point, it is but if you have a UGS packet, it is going to go out first, irrespective of what other flows you have.
That's, yeah.
So in this case, we are limiting the number of UGS packets you have, which are going to the max scheduler itself, because of which you are only seeing this sort of a behavior. And we are, in any case, we are also making sure that you are not saturating the max scheduler. Right. So if you saturate, then things go.
Yeah. So you can't really overflow the queues on the max. No. Neither underflow nor overflow.
Yes, underflow will result in underutilization. Overflow will result in interference.
The other question is, all these things right now, they all of them assume full buffer traffic.
Yes, in this case it is full buffer traffic.
But if it's finite buffer, can you scale the parameters for traffic shaping to handle that?
If you have finite buffer in this case, I can work with the existing setting, but it will result in underutilization. But if I am adaptively able to figure out a load, right, because the base station has a feedback by which you can figure out the throughput going to each client or the load.
The total utilization you can figure out.
Yes, and using that information, right, I can decide how I am shaping, so I can bring these down or increase the levels accordingly.
Yeah, but I guess it might need per slice throughput, per slice availability of resources on the base station. Now the total base station utilization may not be sufficient.
Yes, just that metric may not be sufficient, but I was just thinking maybe just based on load rate on that slice, because it also shows the amount of throughputs and the statistics per client. I could use that to figure out. So in the next set of experiments, this is I think the final experiment in this slot, where we are repeating the same experiment where you have a static client and a mobile client. Only that the static client is sitting in a control room over here. And in the first topology, the mobile client is moving along this path, that is just walking mobility. And in the second and third experiment, the mobile client is moving along these trajectories. So this is just outside Vienna, and this is a GPS trace of the coordinates of the car. We'll be measuring the performance with two metrics. One is a Gen fairness index. So Gen fairness index across groups of flows. And this is a metric which indicates sort of overall system performance. And the other metric is a coupling coefficient. So coupling coefficient is something basically what you see on the client side. So if I was getting this throughput when there was no one else on the other slice, then what is the throughput I'm getting when someone else is moving around on that slice? And in both cases, in both these metrics, I'll be measuring the average performance and the worst case performance. The worst case performance for the Gen fairness index is basically lower. Fairness index is measured from 0 to 1. 1 is extremely fair, 0 is extremely unfair. And it's the same for this guy, but it is the other way around. That 1 indicates extreme coupling across groups, 0 indicates less, 0 coupling. So these are the two results. Let me explain one at a time. So in this case, the first two bars are without our shaping mechanism. Second two bars are with our shaping mechanism. Topology 1, topology 2, topology 3. This is the average performance. This is the max, average, so on and so forth. So what we observe, right, in all of these cases, for this metric, the higher the better, right, the more fairness you have. So you get higher values in all of these cases. You might notice that the average values are very close. That is because even when you go outside, you have pretty decent coverage in most spots except a few corners. That is where the max actually makes a difference. The worst case difference in performance actually makes a difference. So sorry, this is on me. Right? And similarly, you see the result for the coupling coefficient. From the same trace, we got these results. And we see that the worst case performance is improved dramatically, like in all of these topologies. So now I'm going to talk about how intuitively the delay looks in the system, because I talked about airtime and throughput fairness in the system. So the reason I'm saying it's intuitive is because I'm assuming that this is an MM1 system, right? I'm assuming that, okay, if you have two non-virtualized base stations, and then this is an MM1 system, they are being serviced at these rates. And if you have these arrival rates, then the average delay in each of these cases is 1 pi minus lambda, right? So what I want to see is when I'm virtualize this system, and when I'm running virtual base station on top, what is the effective delay I see in the system? So if what I'm going to say is, okay, you had the same non-virtualized system, and now you're putting the same thing on top of a virtualized base station. So you have same arrival rates, and then this is actually the interface which picks up these packets from the virtual base station and pushes them over the wire link to the physical base station. And then this is actually the physical base station. So the total delay is the forwarding delay plus delay you see at the base station. The forwarding delay can be calculated, so if I assume that these variables are independent, then the total delay, average delay is basically 1 by mu minus summation of all arrival rates, which you see at this point. So since this is a wired controller, I'm assuming that if we have a gigabit wired controller, so you will have a very good service rate. So in this case, this delay is very small. The forwarding delay is very small, right? So what matters is the delay at the base station, so basically the arrival rate of total packets at the physical base station is the sum of arrival rates from each of the non-virtualized slices. And if we make sure that the service rate at the base station is the sum of the service rates which you had for individual non-virtualized cases, right? Then basically if you solve for this and if you try to figure out the average delay.
Can you go back?
Sure.
So mu BTS would be
The base station service.
service rate, right? But it will be the same as the mu BTS 1 plus mu BTS 2, would it be?
So that I was about to give an intuitive feel for this after.
Okay.
So in this case, right, if you solve for these, then the eventual delay you see in this virtualized base station will be equal to the, reciprocal of these is sum of reciprocals of each of these. So this basically says that the delay you see with the virtualized system will be actually lesser than what you see with the individual non-virtualized system if you have the same, if you make sure that this condition is satisfied.
So let me ask you the intuition. So if you go to the non-virtualized base stations, right, and you split these slots, so you're providing a kind of fairness. So you have a WiMAX frame, right? Are you saying that if it's 50-50, you just pick 50% of the slots statically and give it to one base station, and the other 50% to another base station? Because then I can see the intuition that you're using user diversity better.
Exactly. So this is just like all this is showing is you will get better utilization of the base station.
Yeah, sure.
If you have. So and because we always think that if you try to do this, so unless if this condition is not satisfied, then you will end up with worse delay performance than what you see on an existing non-virtualized setup.
What's the intuition? What does this condition really tell you?
So this says, right, so if you have a non-virtualized base station which can support 10 Mbps physical, say, max rate, right, and if you have two of these, if you make sure that your physical base station can support 20 Mbps, then the delay which you see on this base station will actually be, with the virtualized setup, will be much better than what you see on individual non-virtualized bases. and you can also compute a lower bound on this service rate, so that you end up with at least an equal performance of the least delay in any of the non-virtualized cases. So this is the intuition, right? And you can calculate this sort of, so you can figure out while deploying your system itself whether this is going to work for your delay requirements or not, based on this model.
So it's just because of better leveraging the user diversity, is that what it is? Or?
Yes. So better utilization on the base station. And that is what we see. And the forwarding delay can be ignored because it's all going on the wired link. So there are other results again, even for this topic on the thesis. We have measurements across different service flows, and there are other design parameters, one use case. So the last part of the thesis is about virtual wireless network mapping. So in this case, basically even before I go to the next slide, what we're going to say is, okay, if you have this virtualized substrate, then how do you do resource allocation across it at different points on the network? So this problem has been looked at in the wired world, where people said, okay, if you have these virtualized routers, and if you have this substrate, then how do you do topology mapping? So this topology mapping boils down to a subgraph isomorphism problem, which has been looked at by others. What we are trying to see is, okay, if you have this virtualized substrate, then how do you assign resources at different points on the network so that you can have capacity for different MVNOs? So there are a few differences that, okay, in this case, like in the wired case, the topology is not important. What you care about is if you have a mesh, then all you care about is the capacity you have from this point to reach to the sink in the network. You don't care about how exactly the traffic is going. So I'll show examples in the next slides. So first question is actually, why do we even need a mapping mechanism? So if you say that, okay, we want capacity at exactly these 1, 2, 3, 4 points, then why do you need a mapping mechanism? But the thing is, the requirements may change over time. It depends on different parameters of the node, like the number of subscribers attached to it. We'll talk about a popularity metric. It depends on the time at which you are allocating these resources. So say an MVNO wants additional capacity for its clients at a certain point, then you could use this mechanism for mapping the resources. This is how our request will look like. So each request, so in this case we are assuming that each virtual request is basically for 3 points of presence or 3 nodes on the network, and they specify 3 parameters: a capacity, a node descriptor metric, and a bid. Right? The capacity is basically the rate which you want at that point, which is in kilobits per second. We are using, so you can use different node descriptor metrics like the one I showed in the previous slide, but here we are assuming that we are using a popularity metric, which goes from 1 to 5. 1 indicates the least popular, 5 indicates very popular. And then the bid which you are making is basically can be computed as a function of the capacity which you want and the popularity. There are different ways in which you can do this. The way we are looking at the mapping problem is, we do it in 2 phases. First one is the provisioning on the network, and then the second part is the mapping of topology. The reason we are doing it in 2 phases is because usually with meshes they are very well planned. So depending on the kind of average loads you see at different points, they come up with the way the node should be deployed and capacity which should be allocated at different points. But since it is needed as an input to our algorithms, we are also going to show how we can come up with basic schemes for allocation. So this topology shows basically a 4-node network where you have these physical layer rates. I'm also assuming that in this case everybody is within carrier sense range of each other. And then I want to calculate the maximum rate which is equal at all of these points, right? Not the rate but the throughput as such, by which I can reach the sink. Right? So for doing that, I'm calculating the effective rate from each of these points. So the effective rate from this node is basically the physical layer rate because there is only one op, so I see 10 Mbps. Same from here. For this node, the effective rate can basically be calculated in this way, that the airtime required to send 1 bit from this hop to this hop is 1 by 5 megabits per second. Right? And then the airtime required to send 1 bit, the same 1 bit from this hop to this hop is 1 by 10 megabits per second. So that is 1 by R1 plus 1 by R2, and that is the effective airtime which is required to send 1 bit. So if you invert that, then you get the effective rate. So that is around 3.3 Mbps, right? So now if you
do some queuing layer to node 2 as well. Is it figured into?
No, that we have not taken into consideration. So we are assuming that, yeah, those things. And yeah. So using these effective rates, right, what we want to do is we want to see the amount of fraction of total capacity which we want to assign to these physical layer rates. So what we want is these fraction of capacities allocated to each of these radios sum up to 1. And then the second thing is you want this throughput rate which you get as multiplied by the effective rate A1 E1 equals A2 E2. So this is basically a linear system of equations. If you solve these, you can come up with the fractions which you need to assign to each of these flows, and then you can come up with the rate. So the maximum rate which we get in this case is 2 Mbps per new. So each of these guys, 1, 2 and 4 can send traffic with 2 Mbps to the same. So there are other things like basically what if the nodes are not within carrier sense range of each other. So we are taking all of those things into account by using interference graphs. And then basically based on the nodes which we select, we can't schedule some other nodes. Those things we are taking into consideration. The second part is basically the mapping part. What we are doing is one approach would be actually doing all combinations of input and checking them on every node and seeing if that works. But instead of that, we are using a greedy approach. So what we do is we select a physical layer node, a physical node, which is suited to us based on the airtime cost to the same, least airtime cost to the same, or based on popularity, because popularity is a metric by which it indicates it can generate revenue, or a function of both of these. And then on top of these, while we are mapping, we'll basically try to do an optimization by combinatorial optimization by running an AppSat on each of these at each of these points. So this is how requests will look like. You have different capacity and different bit coming in from each of these different requests, and then we map these to an AppSat problem. And using this allocation, we can figure out how much we can fit at every node, preferred nodes on the network, and get allocation. I'm going to show some sample results. We have more results in the thesis. So we assume that it is a CSMA radio network, and we are going to show a basic greedy strategy of selection and allocation, assuming there is equal physical capacity available at each of these points in the network.
So what are you trying to optimize? Revenue? Total revenue?
Yeah. So actually in this case, right, when I show the results eventually, I'm plotting revenue, normalized operator revenue. But since the bidding is actually a function of the bit rate which you want, it also indicates the effective amount of capacity which I'm getting. Right. So yeah, this is actually what we are measuring, the revenue and the success fraction. The first experiment will actually compare, so we had a mesh topology on which it was initially all wireless links, but then we wanted to compare the performance which you get with a wired network with the same effective rates, and then also with a hybrid topology where we have two links which were replaced by wired links as opposed to having everything else on wireless. So these are the results which we see. In this case, right, each of these virtual topology requests are for 3 nodes, right, and the request load is generated randomly. So in this case, what we observed is the wired link, the wired topology has a lot of capacity because you have no carrier sense cost associated with every node. And then the second thing is you have no interference across these nodes. So you end up with a much better mapping fraction. And we see that the hybrid case also improves over the basic wireless case, and you get better mapping capability on the node. So actually this will be clear in the next slide where we plot the revenue. What we observe is as the number of virtual topologies are increasing, as the requests we are making are increasing, the revenue, which is normalized operator revenue we are making, is increasing because the failure, the success fraction was almost 1. And then the revenue which you see with the hybrid case is better than what you get with the wireless case, the plain wireless case. So this basically shows that there is a trade-off between how you deploy a mesh network. There are actually better tools for doing that, but we wanted to show this as the first case result.
So if every link is in a different collision domain, they're not in the same collision domain, all the links completely different. So it will be exactly the same as wired. That's
yeah.
So the main difference between this and link,
there are 2 things: carrier sense cost and interference, which
carrier sense cost.
So carrier sense cost is when I'm sending 1 bit across to the next one. I'm not just taking 1 bit of airtime at my node and the next node, but also at 1 bit of airtime at all other nodes which are in CS range.
So that should be calculated as part of the interference cost.
So interference is I'm taking as something else, where basically if you have two nodes which are transmitters and which are not within CS range of each other, so then in that case you have to do some sort of scheduling, or you select one link or the other.
Oh, I see. So even if they're not in the collision domain, you still have to carry some anyway.
Yes, because there is a two-hop protocol. We are assuming that. So in this, the next part of the study, what we are saying is, instead of doing a static allocation in the beginning, we'll do a reallocation basically of the network based on the load which we see at different points, and then again try to solve the NASDAQ. So this is an example. Again, so in this case, what I need to do is I need to assign airtime quotas to these nodes. Say if I want to calculate the max rate by which I can reach from this point, then I need to calculate airtime quotas at different points so that I can get the max rate. So that can be done by basically scaling my airtime fraction by the airtime fraction I get at this point. So basically, 1 by R1 plus 1 by R2 is basically the total airtime I require from getting from 1 to 3. Right? And if I scale that by 1 by R1, which is my airtime fraction to get to the next hop, then I can calculate the weight which I need to assign here. Similarly, I can do a calculation for this point, and I can come up with the weights which need to be assigned so that I get a consistent throughput. Right? So in this case, the value works out to 3.3 Mbps. But the thing to note is that in the equal allocation case, right? So in this case, I got just one node which was getting 3.3 Mbps. In the equal allocation case, I was getting 2 Mbps everywhere. But now if I allocate just this node, and if I get the entire fraction, then I get 10 Mbps as opposed to 6 Mbps. So capacity almost doubles. And we will see this impact in the results, basically when we are plotting this revenue, right? And since the popularity is randomized, right, this essentially indicates the capacity which is allocated on the network. And what we are seeing is the capacity with the dynamic reallocation case increases dramatically. So there is a benefit to be had by doing this back and forth. So in this experiment, what we are trying to do is we are trying to select nodes by a different order, by using just popularity, or by just using airtime cost to the sink, or by using popularity scaled by airtime cost. So what you observe is for the static allocation case, it does not matter because capacity is already allocated at different points on the network. But with the reallocation case, which are these three, you observe that just basically selecting based on cost, you end up picking nodes which have low cost to the sink but don't generate enough revenue. So a better option is actually to go by popularity, or basically popularity inversely scaled the cost to the sink, and then you can come up with a better allocation. There are other results with different topologies in the thesis. We have also looked at 1 or 2 different building schemes. There are so many other things which can be done with this work. So these are the overall future directions. We are looking at some of these right now. And so I wanted to thank everyone for coming for this thesis, my advisors, my committee members, Sanjay, collaborators, well staff, and all my friends, colleagues, and my family.
So Sanjay's like your friend.
Sanjay is my curator. He is a super set of so. Okay,
What are the
Wait,
committee
you say
members?
because you're a supervisor, so you're multiple friends, and you need to go get medical help.
Well, you mentioned the committee members separately, then you can ask, are they your friends or?
Wow, that's a bit.
It depends on how we vote.
So this is the outcome of the work which I did at my lab. We worked on different software projects, and these are being released right now. These are the projects which I worked on other than my thesis projects, and these are some of the publications which I had from these projects. Thanks.